I'm going to talk about adaptive mesh refinement, or AMR. This is a technique to ensure that the mesh has more elements in regions of greater interest. So for CFD, that would be turbulent flow or fluid-solid interactions. But as the simulation progresses, the region of interest can evolve and move around as well. It might follow a moving surface, or maybe a vortex is pushed by the flow itself. So a parallel application, as it iterates through time, the mesh has to adapt accordingly, so we have to repartition to ensure load balance, which was covered by Guillermo this morning. But we want to adapt the mesh on the fly. So that's what I'm going to talk about. And RWH, BSE, Surfax, and KTH have all improved their own applications, own AMR libraries, and I'll talk about them. So with RWTH, their code is Maya, and they use oct trees, which is a regular Cartesian mesh. Essentially, it's a cubic cell, which is hierarchically decomposed into 8 child cube cells, and this recursion happens recursively. So each parent will generate 8 children. If a parent has no children, then it becomes a leaf cell, and neighboring cells are those on the same level. It's just some terminology. So Maya has introduced sensors. These are used to trigger the refinement or indeed the coarsening of a particular cell. These sensors are a numerical device that are placed on grid points, and they sense, at the moment, they sense the magnitude of the vorticity for triggering, for detecting shear layers, and that would trigger a refinement at that region in space. Or they use phenomena that generate entropy gradients, such as shock, which would be shock waves. And the output of these sensors are computed either at a given time step or when a particular condition is met. And it's noted that the refinement or coarsening of a cell is controlled by these threshold parameters, which are based on the statistical distribution of the sensor in the flow field. They find that these parameters are very, the performance of the code is very sensitive to these parameters. So for steady state problems, adaptation is initiated when a specific residual convergence limit is reached. They also ensure that the number of deleted cells does not exceed the number of newly created cells. This avoids this oscillation of number of cells being created. For unsteady cases, the grid is adapted at a regular time interval. Again, it's quite important to keep the number of cells constant. And here's an example of an unsteady case, this particular von Karman's vortex street. I'm going to fly through these here. I'm jumping onto BSE already. What I've done is really taken our best practice guide, which we published very soon, and summarized the advanced, so the AMR section. So if there's any details here that you'd like to know more about, then you can read the publication very soon. So BSE have parallelized their AMR workflow in Alia. I won't mention the stuff in grey here is just the technical summary. But essentially, what they've done is the steps in blue here are is to migrate from one unstructured mesh to the next. The error due to the former mesh is estimated, measures the adaptation requirements, and then the new mesh is generated in parallel. The solution is then interpolated from the old mesh to the new mesh. And then finally, if the resultant domain decomposition has become unbalanced, then load balancing is required. Again, this was addressed earlier this morning. So the error estimate and mesh generation, they've looked at a lot of different strategies for the error estimate. Found Laplacian filters were found to be the most robust, but they did find that the better strategy was problem dependent. And regarding mesh generation, they link with an open source mesh generator called Gmesh, which is quite popular with a lot of the EXCELLERAT codes. And the new meshes generated by Gmesh are based on the error estimate, and the total number of elements in the mesh. So when parallelizing this remeshing, or I guess repartitioning, each parallel process will generate its own new mesh within its own domain. The key issue here for pretty much all AMR codes is what happens at the border or the interface of each MPI ranks domain. So Alia follows a conformal approach, so therefore the interface elements between neighboring subdomains must match. So the solution, if they're going to be updating the mesh within each their own private local domain, is called interface freezing. So the interface elements remain unchanged, and each process adapts just the remaining elements within its subdomain. And then it's iterated, is used to remesh the overall domain, but the interleave interface remeshing and internal remeshing. So we don't loop, so we don't end up with some sort of boundary element numerical diffusion being introduced in error. So parallel 3D so you have to migrate the solution from the old mesh to the new mesh, and here they use parallel 3D interpolation. Evaluation of the coefficients is very expensive. It requires a search through all the elements of the previous mesh. And the load balance requires repartitioning of the new mesh. This was done using a space filling curve. I think this is the Piano Hilbert one that has become very popular now. And an image of flow around this cylinder, Reynolds number 120. You notice the mesh is concentrated around the vortices. For Surfax and AVBP, they've introduced a new AMR process called tree adapt, built on top of the hierarchical domain decomposition tree part, and which, as we've already heard, exploits the underlying hardware. And they've coupled this with an open source mesh adapter called MMG, which is also being parallelized. Again, the stuff in grey is a bit more technical. So the unstructured grids for complex geometries and uses domain decomposition, this is AVBP. Before EXCELLERAT, there's no AMR framework existed, similarly to Alia, in fact. So thanks to EXCELLERAT, they've parallelized their AMR. They've taken the open source MMG library and parallelized it, and now coupled it. They tried two different mesh partitioning libraries. One was Yale's 2 proprietary library, and the second one was a homemade alternative, tree adapt, which, as I mentioned before, was based on tree part, where tree part is a hierarchical mesh partitioning library developed by Surfax for the EPEC project. The new parallel AMR process in AVBP starts with initialization, and then, as with Alia, there's an adaptation step. So again, as with Alia, each processor does the internal mesh, but here they use MMG. Then again, the border elements are frozen, so that they match the elements across partitions. These elements, I should have said, are overlapping cells of neighboring domains. An adaptation is triggered via a user-defined metric stored on the mesh vertices, somewhat akin to Maya's sensors. Now, the two libraries that were tested, Yale's 2, at this point adds an internal loop at the individual domain level to the skewness of the adaptive mesh is checked, and further adaptation is required. Tree adapt skips this, as this is not required by AVBP's explicit solver. The second part is followed by the solution interpolation. Yale 2 uses linear interpolation, whereas tree adapt uses least squares. And finally, the load balancing. The previous frozen frontier elements are weighted to ensure they become internal elements for the next adaptation. So they have a slightly different tact on boundary elements as compared to Alia. Finally, KTH and NEC 5000. KTH has developed an AMR framework. With NEC 5000 is a spectral element, whereas the previous 3 were all finite volume, finite element. So spectral elements are these small regions spanned by Lagrangian interpolants. The AMR method here does not employ remeshing. Instead, they increased the number of degrees of freedom by increasing the element count. So they kind of refined the mesh on the fly. And so the AMR exploits existing domain decomposition of the spectral element method. So it increases the number of elements, as I just said. There's no remeshing. Simple oct-tree slipping of each element. Unlike Maya, which was a regular, this was, of course, this is an irregular mesh. This has advantages over, for instance, local variation of polynomial order, a smaller constraint on the Courant-Friedrichs-Lewy condition, and more localized refinement on as the octree can be recursively refined. There is a disadvantage, though, in the introduction of so-called hanging nodes. So what they've done to solve this was to modify the solver by adding an interpolation operator at the non-conforming faces. It introduces some work imbalance, but in practice it's negligible. And indeed, both conforming and non-conforming solvers share the same parallel properties. So conforming space, non-conforming mesh. AMR can generate non-conforming meshes. Of course, this is the at the boundary of MPI domains. So data transfer, for conforming meshes, it's simply a copy, which is fine. Non-conforming meshes require a special operator connecting these elements. This is called a mortar element. KTH has simplified this by retaining the initial conforming mesh and using a restricted form of the adaptive mesh refinement. So instead of a copy, they use interpolation. This avoids complex data treatment between mortar elements. And they've constrained the refinement freedom. It enables simple and efficient mesh managers to be employed, which is positive. And then use for one example is the P4S library. But in practice, conforming space non-conforming mesh is not a real limitation. There's a significant reduction in the simulation cost. So I believe this is my ultimate slide. Removing mesh management from the solver. So they've separated the mesh management out of the computational kernel. Using P4S provides the CFT solver with all the information needed to construct the mesh using child elements only. All parent-child relations are hidden. In fact, in this case, the parent elements are not even stored. So this reduces any modifications required on the application itself. It allows for an optimal solver setup for each mesh. There is a cost overhead, of course, the solver restart for each mesh modification, but it's really dominated by the cost partitioning and the coarse grid solver setup. This cost overhead, however, is only noticeable when your MPI rank count is over tens of thousands of cores, which of course in Exascale is exactly the territory you're in. So the NIC 5000 MAR works very well for a steady state mesh. Final steady mesh can be reached. Includes multiple statistically stable flows cases, but at the present it's not well suited for tracking flow features. Okay, this is my penultimate slide. The error estimates, as we've mentioned for the ALIA and AVBP, are critical for reducing error and minimizing cost. KTH have introduced two new tools. First is a goal-oriented adjoint error estimator. So there's significant overhead, problem with turbulent flows. Think of adjoint as going forwards and backwards in time, then turbulent flows are chaotic. Then if you go backwards in time, it retains its chaotic nature, and as you say, as one says, you can't unscramble an egg. Okay, I'm going off topic. There's also a spectral error indicator, which is used in most NIC 5000 production runs, provides a sufficient mesh quality. So to target turbulent flows, KTH are currently developing an error estimate based on transfer entropy, measuring the causality between quantities of interest, like drag or lift, and flow variables, velocity, pressure, etc. So, final slide. Great success. New MR allows previously unaffordable hi-fi simulations, like wingtips, simplified rotors, for instance. And this picture here is the AMR mesh structure for the simulation of the flow over an NACA 0012 wing profile with rounded tip, that famous wing profile. And that's it. Hopefully I've kept the time.
Yes, very well. Thanks a lot, Gavin. Yeah, quite nice overview about the techniques that were introduced in the codes. And yeah, I think AMR is definitely the way to go, as generating a static mesh of a constant resolution is definitely no longer the way to go if you think about mesh sizes and stuff like that. Currently, I cannot see any other questions on the chat, so I would take that forward to the Q&A section at the end, since we have to keep our time schedule to have Claudio at the correct time slot. So I would now give the stage to, thanks a lot, Gavin, again. I would give the stage to Christian Gscheidle from Fraunhofer SCAI, who is currently working on his PhD and in the area of high-performance data analytics and how to apply that to simulation result analysis. And Christian will today talk about in-situ data analytics and how to explore simulation during runtime. So Christian, please, stage is all yours.
Thanks a lot for the introduction. All right, then welcome also from my side. So what I want to do today is talk about in-situ data analytics and show some workflows, software tools that we have been setting up in EXCELLERAT, and also show 2 examples of how that was applied to turbulent flows. So the general kind of goals for data analytics in large-scale simulations is, on the one hand side, if we run already these expensive simulations that contain a lot of information, we want to make sure that we extract as much knowledge from it. And that could be in a lot of different forms. For example, physical insights by computing global modes. It could be surrogate models for consecutive like optimization or multi-fidelity optimization task and so on. And on the other hand, we also try to support the simulation process itself, kind of making it more efficient, which again could be in different forms, such as identifying regions that are most interesting or relevant for AMR, or also that should be considered more for post-processing. Or another example, providing stop criteria for the simulation if it goes into a wrong direction or if we have enough time steps and so on. And the biggest challenge with large-scale simulations, of course, is the pure amount of data that we have to handle, and also the high formal dimension of the data. And this leads to 2 basic technologies that we have been using a lot in this context. On the one hand side, it's the in-situ analysis, which actually originated in the visualization world, and we've heard about that already yesterday from Dennis, related to in-situ visualization in Visual. And for data analytics, it's quite an similar motivation. We have a lot of data being generated during runtime, and we can only store a small part of that to disk. So there can easily be 3 or 4 orders of magnitude in between. Now, for data analytics, there's actually a second motivation also, because if we run an in-situ analysis, then we can look at intermediate results during runtime. So we can exploit that to kind of follow the simulation or run a simulation monitoring during runtime. And so the biggest challenge here is that not all algorithms can just be transferred into an in-situ way. A lot of algorithms just need the whole kind of time series at once, or have to run multiple times over it. So that's the one challenge. And on the other hand, we have also, of course, the software side to have efficient interfaces through the simulation code. And the second technology would be to use data-driven analysis. They have some advantages when it comes to a more global perspective onto the data, and also applying them automated if we are not completely sure what to expect during runtime. They are more flexible in that sense. And yeah, but should not be seen as kind of a replacement to an like more physical or a quantitative analysis. It's more like an addition to extract even more information from the simulation. Now, to set this up in a realistic workflow, we developed an in-situ framework, and the key requirements there were, on the one hand side, the flexibility of the framework, which is necessary if we develop algorithms. So we want to kind of be able to connect to any kind of data analytics library that already exists. They usually have a Python API. So this is kind of the one requirement, and on the other hand, of course, also being efficient. And this is a lot of times very contradictory. So kind of bringing these together, flexibility and efficiency, was most challenging. And of course, we also want to connect to standard libraries and be independent in that sense of a flow solver. So the typical workflow here could be based on ParaView and Catalyst. They also originated from the visualization world, but can very well also be used for data analytics and can be connected to a lot of different codes. In this case, it's NEC 5000. It could be any other code as well. And we usually then have an online part in form of a VTK pipeline or Catalyst pipeline, where our in-situ algorithms are wrapped as VTK filters, and in the core, the algorithms are just kind of Python classes. So any kind of analytics library can be plugged in there as well. And then usually after the simulation, there's also an offline part that could be run again as a plugin in the ParaView GUI. So the first example that I would like to show stems from a collaboration between KTH and Fraunhofer. It's the in-situ estimation of time averaging uncertainties in turbulent flows. So what we usually see is we have some time series that comes from a turbulent simulation. There's some initial phase, and then there's an interval over which we want to compute the time average values. And the problem here is that we don't know the original like continuous signal, but we only have samples at certain discrete points. So the sample mean actually is biased with some uncertainty due to finite time sampling. And the longer the simulation runs, the more accurate the results get, or the smaller the confidence interval. But of course, runtime is also expensive. So we want to keep it as short as possible, but long enough to get confident results. And this actually motivates an in-situ analysis, because then we can kind of estimate this uncertainty during runtime and then decide when to stop the simulation. But there's also a second motivation for an in-situ analysis. That is that we can handle a lot more data. So if we run this offline, then we could only do this at a few spatial points. And in an in-situ analysis, we can basically run this at any point and then get a completely three-dimensional picture of the quantities as well with the confidence intervals. Just to summarize real quick the approaches that already exist there. On the one hand side, we have the batch-based methods that rely on the idea that we cut the whole signal into smaller batches and then assume that these batches are not correlated anymore. So we can just use the variance over the means to compute the uncertainty, which is quite computationally efficient, but not so much confident. So there's a bias with respect to the batch size, and the correct batch size is actually not known in advance. So the more sophisticated approach here would be modeling the autocorrelation function. And this again is more accurate, but also more computational demanding. And there has not been an updating version of that. So this was where our collaboration actually focused on, to turn this modeling ACF approach into an updated version. And I don't want to go into details here, but what we are basically doing is to compute the ACF at certain lags in time, and then use that to fit a curve through it to get the complete ACF function, and then again use this equation 1 to actually get the uncertainty that is corrected by the autocorrelation. Yeah, so this has been applied to a turbulent flow around an airfoil. What we are interested in is, in this case, the mean velocity field in the midplane and the uncertainty that is attached there due to finite time sampling. Right, so just a quick overview of that. We compared the existing batch-based methods on the left side and our IMCF approach on the right-hand side. And what clearly can be seen is that these batch-based methods depend a lot on the batch size. And actually, this batch size, it's not known a priori. So usually, if you would apply this in situ, you had to kind of set up a lot of different instances with different batch sizes to eventually get the right one. But so our IMCF approach is much less influenced by these kind of hyperparameters. And it compares very well to state-of-the-art offline techniques, for example, based on autoregressive models. Then in a second example for an in-situ analysis would be proper orthogonal decomposition. This is usually computed it has several motivations. The idea behind this is to have a matrix of snapshots that is decomposed into spatial modes and temporal coefficients. And usually the majority of the energy in the signal can be expressed by just a couple of modes. So the data can be reduced a lot, and also the modes are very interested from a physical perspective to get a better understanding of the flow physics. And this could also be combined with a linear dynamical model for prediction or further analysis. And what I want to focus on is an application for an in-situ monitoring, basically. And so one of the major challenges here is to bring together the parallelization of the algorithm and the streaming version. And the approach that we took in this case was to take advantage of already the decomposition of the flow field that is naturally given by the solver, and then run local PODs on these local meshes in a streaming way, so they get updated throughout the simulation after a couple of time steps, and eventually take those local matrices to then construct a global POD. And so the advantage here is that it's quite efficient because not a lot of communication is needed between ranks, but also also the memory usage is constant because only some batches are cached and then constantly updated throughout the simulation. So the number of time steps that are processed is basically not restricted. So this brings me to the final slide of an example for an application of this in-situ POD for simulation monitoring. So what we're looking here at here it's a bundle of simulations, so some parameter study where each point belongs to one simulation, one time step. And we compare a certain mode and how that develops in time. And can clearly be seen that there are two kind of branches in which the simulation goes, the left and the right branch. And at the end of the simulation, we actually see a difference here, that there's a separation of the flow behind the round, which is not present here. And the interesting part, in my opinion, is that these kind of branches can be identified quite early, in an early stage during runtime, even though only from a visual perspective, there's not really a difference between the flow fields during that time. So if you're actually saying one or the other is not wanted, or we want to maybe avoid a separation here, then we could actually abort all the simulations from the left branch and eventually save all the computing time here. But yeah, so there are other applications for monitoring to identify, for example, outliers or some unwanted behavior, also wrong numerical settings. You would also usually see that this point would lie somewhere outside of these other simulations. Yeah, that's it from my side. Thanks a lot for your attention.
Yeah, so now I think Claudio is on the call, isn't he?
Hello, good morning.
Hello. So yeah, welcome, Claudio Scalese from the EuroHPC joint undertaking. You didn't hear it, I already did your introduction, so stage is already all yours.
All right. Thank you very much. So unfortunately, I don't have, I saw your agenda that you will have the Q&A just after my presentation, but I'm switching from one meeting to the other, so we'll try probably right after my presentation to have a question and answer, if any.
Yes, we will do that, of course.
I'm going to introduce my presentation. Do you see my screen?
Yes.
Okay.
Works.
So again, my name is Claudio Scalese. I'm Junior Project Officer at the EuroHPC Joint Undertaking, and today I would like to talk to you about the Centers of Excellence for HPC application within the new R&I program Horizon Europe. So basically, what I would like to start is with the new program Horizon Europe, since the first, let's say, legacy of EXCELLERAT was funded with Horizon 2020. There is a new program in action, that is Horizon Europe, that supports research and innovation through work programs, which set out funding opportunities for research and innovation activities. So as you can see, there are three main pillars that are defining this program. That is pillar one with excellent science, pillar two with global challenges and European industrial competitiveness, and pillar three with innovative Europe. So basically, Horizon Europe is a program that is really delivering on EU policy priorities. The strategic plan sets out a strategic orientation and impacts areas for research and innovation investments under Horizon Europe for 4 years. The key strategic orientation and impact areas are formulated on the basis of expected impacts. The difference also with Horizon 2020 is that there will be more strengthened link between the priorities of the EU with the project results that they should come out with the proposal that will be funded. And each expected impact is targeted via dedicated packages of action in the work program. These are termed destinations because they indicate both the specific direction and the ultimate point of arrival of the projects to be supported through Horizon Europe. The work programs include the research and innovation activities to be funded under Horizon Europe for 2 years. So going more on the details, so as we were saying, Horizon Europe is implemented through work programs, which set out funding opportunities mainly through call for proposals. A call for proposal will normally contain one or more topics with a common deadline. The budget of the call is distributed among topics where topics share a budget envelope. Proposals for these topics will be competing against each other and will result in a single ranking list. So applicants are applied to a specific call and topic, and each topic will have to include a scope, an expected outcome, an expected impact of the destination to which the topic belongs, the type of action, and the topic budget. So, as we were saying before, the approach is more like bottom-up. So there is a strengthened link between the policy priorities and the project results in Horizon Europe. So as we can see, there are key strategic orientations on impact areas that are going to define which are the main themes that they are going to treat in the project to be funded. There will be expected impacts that are in this program called destinations, and the expected outcomes that are the topics that they will match with the project results that are coming at the end of every project. Here we have some glossary terms, so an idea about what we request from the different projects. So for impacts, objectives, outcomes, pathway to impact, research output, and results. So now for the second part of the presentation, I'm going to focus on the call that we launched on Centers of Excellence for HPC applications. So the idea that is behind this call is because upcoming HPC architectures require significant developments. So for sure, to improve the scalability, that it's an important asset for the new HPC applications, the modular and heterogeneous architectures, resilience, and complex workflows potentially using different types of HPC resources. What we will focus on the activities that are behind the COEs are to prepare science-driven HPC application for the European HPC infrastructures. So this requires efficient and sustainable software development, strategies for legacy code, effective quality management procedures for contribute code, automated testing and deployment strategy on the EuroHPC infrastructure. Here is how it's configured and the budget. So the overall budget is 90 million, that is split in two parts. It will be 45 million for the EU contribution, and the other 45 million that will come from the national contribution by every national funding authority. There is an option that we've been envisaged also that in the future the EuroHPC will entrust the guarantee from the national fundings to also release the other 50% of the funding rate, but this is still at an early stage. So for the moment, we are the consortia are the ones that they have to apply for the national contributions and follow the procedure. So for every topic, we have a minimum EU contribution 50 million, and the final decision on the allocation of funds will be made by our governing board and based on the ranking list of the proposal received. So the call is split in two topics. First one is Centers of Excellence preparing application in the Exascale era. and centers of excellence for supporting supercomputing application for science and innovation. To remind also that any spent EU fund will not be lost, but it will be used for the next HPC calls that we will launch in the near future. So regarding the scope and the objectives of the COEs for the HPC application, these are research driven, even though scientific research is not really within their scope. The COEs are expected to serve the European HPC communities and support European R&I and I. Examples for research-driven activities are technical implementation of complex workflows to support heterogeneous HPC architectures in collaboration with scientists and user communities to provide data and real use cases, or implementation of state-of-the-art software development cycle and testing infrastructure to ensure effective quality management of contribution from the scientific community and address legacy code. Example that they could be beyond the scope, not really relevant for the projects, are staff funded by COE carrying out fundamental research as leading author, and activity related to HPC application control and primarily used outside the eligible countries. So going to the call topics. So the first one, the centers of excellence preparing application in the Exascale area. This is mainly focused on the Exascale challenge and selected European flagship application with high impact of European research and development innovation, in co-design collaboration with the European Technology Initiative to support future European Exascale HPC architectures and infrastructure. What is considered out of scope, as I was mentioning before, activities that focus on HPC technology and application outside eligible countries with little European added value. This is really important to strengthen the fact that we are focusing more on really the eligible countries and the European added value. Applications without credible and justified Exascale ambitions and perspectives. So we need to really prove that the applications are really focused on in the call, and application where the use of Exascale resources offer only marginal benefits. For the second one, we have the centers of excellence for supporting supercomputing application on science and innovation. This is really focusing on HPC application requiring peta and pre-exascale resources, supporting broader communities, streamline and professionalize HPC application development efforts by communities, and to bring on the key of the action also the SMEs that are the backbone of the European Union community, industry and partners based in eligible countries that are currently developing their HPC infrastructure and ecosystem. So again, the same as for the other topic, what is outside eligible countries with little European added value would be less considered. We strengthen the fact that we need to focus on the HPC resources. Researches such as funding of PhD thesis, fundamental science, use cases without HPC application development as the central motivation and objective are not really in the scope of this call. For more information, we rely on the Horizon Europe program guide and the general annexes of the work program. And from my side, I would like to thank you for listening to me, and I'm open for questions from the floor.
Thank you, Claudio, for the overview about what's in the scope and what not. This was quite an interesting view on the topic. And as we currently have no questions on the chat, I would like to ask, so this morning we had Julian from Safran Aircraft Engines here explaining what's really needed if you would to take forward HPC applications to the industry, and that there's a special development needed to ensure the credibility of the code, the correct maintenance and stuff like that. So is it correct that you see the centers of excellence more or less in that position to take the academic codes forward to be applicable for also industrial problems?
As I was saying, what we are looking on the call for the center of excellence is really to bring an added value for the industry, in special case in the SMEs. So the idea is to strengthen the link between the community and to bring also the industrial users that are our end users most important for our activities. So for sure, we need to focus on what the HPC application can bring an added value for their day-to-day work. And I believe that strengthening the collaboration and also developing interesting proposal that they are going to create a platform on the HPC platform in Europe would bring for sure a huge benefit for the community.
Okay, thanks. And here we have a question from Solan Horvath. Are there events planned to introduce open EuroHPC calls that are, I guess, should be kind of complementary to the actions in the COEs, right?
Actually, we had some events already in the past, like the EuroHPC Summit Week in Paris that was in March, but also there will be new events that will be organized. So the idea is always to check our website that is publishing our main information, and also on our media channels that they are going to inform also the stakeholders about all our events. Let's say that we don't have like a main event where we will be advertising all our calls, but we will be part of some events, collateral events that they can where will be discussed our activities. So the idea is to check our media channels and to keep updated.
Okay. Thanks a lot for the insights. And with that, I think we have no more questions. So again, thanks a lot for your participation and the introduction to the scope of the calls. And hear you soon, hopefully.
Thank you very much. And it was a great pleasure to be here with you today, and wish you the best of the continuation for the meetings.
Thanks a lot.
Thank you.
And with that, I would now hand over to Nick Brown, also from EPCC. He's already since 2012 at EPCC as a research fellow, and he received his PhD at the University of Durham for exploring novel programming abstractions via the type system for writing high-performance parallel codes. And at EPCC, Nick is also working on the novel architectures as future hardware for HPC. And with that, it's perfectly nice that he's today talking about FPGAs for HPC workloads, the why and the how. So Nick, please go ahead.
Thank you very much, and hopefully you can see my screen okay, my slides.
Yes, perfectly nice.
Perfect. Excellent. Well, thank you for the introduction. So my name's Nick, and during the EXCELLERAT Centre of Excellence, I've been exploring novel architectures, specifically FPGAs, and the role that these might play in the future, both in terms of accelerating, but also reducing the power usage of our different workloads in our supercomputers. And just so we're all on the same page here, what I'm talking about with this architecture is where the electronics of the chip is directly configured to look like the application. So you no longer have the black box microarchitecture that we have on CPUs or GPUs. Really, the name of the game is configurability or specialization, where all these red things in this diagram are configured, as I say, to look electronically like the application. And we've got a whole bunch of other things dropped in here as well, such as, for instance, very fast memory like level 1 cache, but crucially I can use it exactly as I need to for my application. Things like acceleration for floating point arithmetic, and then lots of high bandwidth connections to the outside world. And slowly these things are gaining some traction in HPC. There's different testbed HPC systems out there that make this technology available. So interesting to see how we can use it for our applications in the future. But I think crucially the question becomes, well, when would we choose this technology in combination maybe with something like CPUs and GPUs? Because my view on this is if your application is compute bound, then forget it. You know, pop it on a GPU. We heard earlier the great GPU work that was completed. Those are a really good match there. But if there's other issues with your code, for instance, if your code is stalling with core bound issues or maybe these memory bound issues here, then potentially that's where this specialization is really helpful, because we can specialize the architecture to suit exactly what we need rather than rely on the general purpose assumptions by some of these other technologies. So for instance, we might get something like this down here, where in blue and in red, we've got the compute going on, whereas in here in green, we're feeding in the data. In here in yellow, maybe we're reorganizing the data, all in tandem, all in concurrent activities in order to keep that compute fed. So that was really the idea to explore and to see how that would play with some of our applications and use cases in the Centre of Excellence. So very briefly, the first thing that we looked at, and we've heard about it previously during the workshop, is NEC 5000 and its proxy-app Nekbone, where we are iterating over a whole load of elements. And if you look at the overall runtime of the code, the majority of the runtime is within the CG solver, and when we profiled it, a lot of this is memory bound and core bound. So the theory was, well, by bringing this onto the FPGA, by moving to this data flow approach, can we turn the red into green? Can we fix these issues potentially? And it's a bit of a journey with these sort of technologies. Maybe this isn't a great surprise compared with things like GPUs as well, where we initially have our performance on the CPU that we've baselined, and then we move it onto the FPGA and it's utterly awful. And then we've got all these different activities within a single kernel perspective to then suit it for this data flow architecture, to then go from super duper slow to much faster on the FPGA. And very briefly, I just want to give a very brief overview of some of the different bits and pieces that we found with our codes that really make an impact here. The first thing that we tend to look at is working top downwards. So reorganizing the algorithm from the high level perspective. So for instance, here, composed of lots of different matrix multiplications. We are breaking these apart, having these as different regions across our FPGA chip that are all running concurrently and streaming data between them. So they're all running at the same time with data being streamed between them, with the golden rule of keeping data flowing through the chip and each cycle. And that's okay, but it's not sufficient on its own, because what we also need to do is to go into each of these boxes and optimize bottom up, optimize exactly what's running within each of these independent regions that are there concurrently. And that's where we're playing lots of different tricks, things called pipelining up here, where each of our individual loops are spread out around the logic, so we can feed in a new iteration every cycle and get these things running concurrently. We unroll our loops to give us effectively vectorization, but then also below the red line, we've got some negative aspects that can really impact our performance, where, for instance, we're not getting a new loop iteration processed every cycle and we're losing performance. And the reason for really showing you this is what can then happen is our code moves very substantially from the CPU version to then the optimized FPGA version, playing these games to keep that data flowing in order to get the performance. And that can make a big impact in terms of what we're getting compared with what we got before, but then we can sometimes have to go even further. For instance, here we found that the algorithm was running in phases for these different parts just due to data dependencies. So then we have to put in data buffering and running the different parts for different elements concurrently, feeding one to the next. Again, moving further away from the initial CPU version. But on a single kernel perspective, it's worth doing this because eventually you get to pretty good performance out here. And this is just on a single kernel perspective. We can then scale this up to multiple kernels that I'll talk about more in a moment. What you can see also here is we've got this theoretical performance. And I think it's fair to say on a CPU or a GPU, you look at what the manufacturer promises you'll get, and it's all, who knows? You know, actually what you get in reality is quite different from that because of this black box design of the electronics. Whereas here on this FPGA, it's much more realistic, I think, to theorize about the performance and then potentially see how far you are away from getting this. So what we're saying here is, look, based upon our design, this is the best theoretical performance we can be getting without changing the design. Well, how close are we to this? And if we're quite far away, well, potentially our design and our bottom-up optimizations aren't that good. We need to improve it. If we're getting quite close, then there's just less of this low-hanging fruit to gain here. So what we did with this is we then scaled up the number of kernels, and we then compared this against our 24-core CPU and V100 GPU for single, double, and also half precision on the FPGA. And what you can see is we beat the CPU hands down. The GPU is a tough test in terms of performance. For double precision, certainly for the larger problem sizes, we are falling short. But when we go to single and half precision, we can use more kernels on the FPGA and we're getting better performance. And this goes back to what Gabrielle was talking about before in terms of it's not just about the performance, but also about the power efficiency and using the energy fed into the system most effectively. And this combination of much lower power draw by the FPGA, but also reasonable performance as well, certainly for some of these different reduced precisions, can actually give us some nice power efficiency compared with the GPU and the CPU. So that was Nekbone. Just very, very briefly, we've also heard in lots of detail about Alia, fantastic code developed by BSC. I know it's been one of the many highlights of the Centre of Excellence working with Alia and all the improvements that we've seen with the different activities reported in the workshop. We focused on the incompressible flow part of Alia and specifically building up the matrix around this, where again a lot of the work on the CPU was wasted. Only about half the cycles were doing useful work. So again, this theory of, well, can we bring it over to the FPGA, this idea of specialization to turn the red into green. Exactly what I talked about before, this combination of top-down optimizations, which are here, and also bottom-up, playing with this different ordering of the data, it's in yellow here, and how we do these different things. But here what was interesting is this was okay, but you can see actually there was still quite a bit of performance still to be gained compared with the runtime on the 24-core Xeon CPU. And here the big challenge was actually how we were feeding data into the FPGA. And we had to move quite a way away from what we'd assumed initially and do quite a few enhancements around the way that this is working with the FPGA in combination with the host to work in different batches to again keep the electronics fed with data, this golden rule of keeping the data flowing through. But when we did this, we had significant performance improvement compared with the CPU, again just for one single kernel here. And then with this again, we scaled up the number of kernels. We could fit on 3 matrix assembly kernels for Alia onto the FPGA. And then we compared this again against the 24-core Xeon Platinum CPU and the V100 GPU. And similarly with Nekbone, the CPU is really easy to beat here, irrespective. The GPU is a much tougher customer. But here, as we're going to the larger benchmarks, then the FPGA is much more competitive in terms of the performance. It's edging ahead, certainly with this largest benchmark here, whereas compared with the V100 GPU, it's just falling slightly short here. But compared with the CPU, we are, as I say, way ahead. And then on the right, we've got the power efficiency. And this is the combination of the performance and the much reduced power draw. And again, as you can see, the FPGA is significantly winning here compared with the other technologies. So I've gone through that very, very quickly because I appreciate that, as the last speaker, we've got the Q&A that we want to get onto and want to talk about. But really the point of showing you this and the point of the work is to look with some of these different use cases and really to understand where we might use the technologies and some of the techniques as well that we might use here. One of the nice things about the Centre of Excellence is we've done quite a few publications on these different things. So I've had them throughout the slides if you're interested with much more information on there. I think absolutely it is worth considering these sort of technologies, but you have to pick your battles and you have to really understand what they're going to give you compared with the CPU and the GPU and what you're looking to fix potentially. I am super duper excited, the thought I will leave you with here, because the next generation of FPGAs have these things called AI engines. And these are vectorization engines combined with that reconfigurable fabric, which give us massive performance for floating point arithmetic. And I say the next generation hardware, we actually had some delivered to EPCC yesterday, so they are absolutely hot off the press. And I think taking what we've got and combining it with these AI engines and that fabric in this next generation of FPGA will potentially help push these things further and might be the difference that gets us beyond the GPU performance that we're currently seeing potentially. So thank you very much for listening. That's my time up. But if anybody's got any questions, any discussion points, please feel free to ask or raise them.
Thanks a lot, Nick, for this quite interesting overview. Currently, we have no questions in the chat. If someone has one, please paste it. So I will postpone mine that I have to your talk and first give Swaroop Kanapuli the chance that his question he has to Christian Gscheidle. And the question was whether the IMACF method to be used can be used for the to test convergence of a certain simulation that seems that it is converging visually, but is not the convergence is not completely sure. Do you think that this method can differentiate between these two cases more precisely?
Yeah, thanks for the question. I think it's actually quite interesting to think about that. And so in general, I would say the method would not distinguish whether the uncertainty is due to the physics, like turbulence or like the chaotic nature, or due to numerical uncertainty. So this would be kind of combined into the overall statistical uncertainty. So to answer the question, I would say it's yeah, maybe indirect. So you would probably observe the confidence intervals going down, decreasing more slow than if there was like no numerical error. But also, as Sali has actually explained yesterday in his talk, if there's a constant error, for example, due to numerics, then this is actually not uncertain because it's, yeah, there's no uncertainty attached to a constant error, so that would not be detected. But otherwise, I would say yes, so in an indirect sense. Yeah. Thanks for the question.
Okay, thanks a lot for the answer. Actually, I have also a question for you, Christian. Do you already employ the kind of heterogeneous HPC architectures for your approaches, so that the basically the evaluation is done for on an accelerated cluster part, and the actual simulation is run on a different one, or is it yeah, work for the future?
There is some work going on right now in this direction. So basically in yeah, two directions. First, that the in-situ analytics is run on different nodes than the main simulation. So kind of in an asynchronous way, which has a couple of advantages. But yeah, regarding GPUs, we are not that far really. So yeah, it could have some advantages, but yeah, we have to see whether it really is like underlined if it's in like speed up, because a lot of data then also has to be shifted in between and so on. But there's some work going on actually at KTH also, and yeah, some collaborations.
Okay, thanks a lot. So keep the fingers crossed for our second funding phase. So we will see then how this works out.
That would be a good topic for that. Yeah.
Yeah. Okay. Thanks, Christian. And yeah, Nick, looking at the power evaluations, the power efficiency of the FPGA, that's quite impressive, of course. And I mean, this is kind of the strong thing about this technology, right? And for that, I have a different question. How's it with the kind of economic efficiency? So can you compare the kind of node price for an FPGA accelerated node versus one for, I don't know, a V100 or A100 accelerated node?
Yeah, I mean, it's a very interesting thing in terms of what I tend to find is the idle power can be a bit higher. So the key is to keep using them. But then when you're using them, I very rarely find our alveos go above sort of 50 watts, even with, you know, really high throughput going through them. The cost of buying these things, I can't remember the exact prices now, but you're looking, you know, 6,000 or 7,000 euros for an alveo from Avnet or something like that. So they are comparable probably to a GPU. I'm not sure what a GPU would cost to buy. So I think they are comparable, broadly speaking, in terms of the purchase price. I guess, you know, to some extent, of course, it is important, but you know, I can imagine a lot of the cost comes from the power usage as well, when it's continually being used.
Yeah, yes, of course. I mean, this is always the question, or the paradigm that computing time is much more cheaper than developer time, right? I mean, you have to invest quite a bit of development in these kind of things. But I mean, if you really turn to Exascale and using system at the 20 megawatt power level, the question goes the other way around, in my opinion, right? So developer time is much cheaper than it is the computing time, if you really target the hero type runs using the complete system.
Yes, and I think the other thing is, what do you call HPC? We are obviously assuming we have an EXCELLERAT, the data center HPC, but what about if we include the edge and we start to think about doing some processing, in the car, for instance, before it comes in? Well, actually, potentially there, the energy side of things is also very important.
Yes, of course. Yeah. And from your experience, do you think the compiler technology is developing in the direction of FPGA? So basically that the compiler is sooner or later able to take over the optimizations from the algorithmic point of view?
There's two challenges at the moment. I mean, the first big challenge is the compile times. I mean, it's crazy, right? I mean, a compile time can be like 24 hours, sometimes even longer, 2 days. So you imagine our flow as a software developer. I do a few tweaks. Let me see if it works. Well, I've now got to wait till tomorrow or the day after to get the answer. It's slightly easier because you can do other things like emulation, but that is a big challenge. The other challenge is on the performance and all the hoops you currently have to jump through manually. I think this comes back to, I think maybe it was Gabrielle mentioning it earlier, I think this comes back to domain-specific languages and raising the abstraction level so we have more information that the compiler can work on. It was certainly mentioned earlier by somebody. And I think that's a really important part for this and how we can maybe enrich, not just for FPGAs, but for all these technologies.
Okay. Yeah. So thanks a lot for all the valuable contributions. We have no more question on the chat, so I think everything's cleared out quite nicely. Right?